Let's talk about the different mesh refinement options Floefd has. The automatic option in the global mesh defines the initial resolution of the basic mesh in regards to the number of cells in the X, Y, and Z directions. In order to access all of the refinement features, we need to set the global mesh to manual, or else make use of the local mesh items. The only difference is that the settings in the global mesh will apply the selected refinement settings to the entire mesh in the computational domain, while the local mesh items will only apply the refinements to the selected areas within the definition. First of all, in the global mesh, we can specify the number of elements or element size we desire in each of the Cartesian directions. We can also select the Control Planes button to add planes in the different directions, to select the number of cells or cell size, or to modify the growth or shrink ratio between the different planes or intervals defined. The control planes or control intervals are typically used in aerodynamic simulations in order to better control the cell size local to the model geometry relative to the generally oversized computational domain, for instance, a wind tunnel simulation. Regarding the local mesh items, we can use selected parts, components, edges, or surfaces as the basis of the refinement locations, or perform the refinement within a dummy geometric location or volume, such as a cuboid, cylinder, or a sphere. Now, let's actually talk about the different mesh refinement features. First, we can perform the refinement directly on the different cell types we have, meaning fluid cells, solid cells, and partial cells, also known as fluid-solid interface cells. Next, we have the channel refinement. This will perform the refinement within channels, where a channel is considered a fluid path where a pair of opposing surfaces are facing each other, which is why we can modify the minimum and maximum heights of the channels that need refinement. Then we can input the number of cells per channel we aim to achieve, and the maximum level refinement that we will allow Floefd to use to achieve that number of cells. We also have the equidistant refinement. This feature allows us to create shells of refinement at predefined different distances from the selected part. We can control the maximum level of refinement and the uniform distance from the starting geometry at which each zone ends. We can define up to 3 different shells. Lastly, we have the advanced refinement features, which can be useful in some specific situations, such as the small solid feature refinement. A solid is considered small when its size is less than that of a single cell. Thus, we can let Floefd know the refinement we want for this type of solid. Then, we have the curvature refinement level, which is the maximum level to which the cells will be split during refinement until the curvature of the solid-fluid interface within the cell becomes lower than the specified curvature refinement criterion. The curvature refinement criterion denotes a critical angle, and if that angle is exceeded inside the cell will be split in accordance with the curvature level refinement. Lastly, the tolerance refinement allows us to control how well and with what tolerance mesh polygons approximate the real interface. Any surface is approximated by a set of polygons which vertices are surface's intersection points with the cell's edges. This approach accurately represents flat faces, though curvature surfaces are approximated with some deviations. The tolerance refinement criterion controls the precision of this approximation. A cell will be split if the distance between the outermost interfaces point within the cell and the polygon approximating this interface is larger than the specified criterion value. The tolerance refinement may affect the same cells that were affected by the small solid refinement and the curvature refinement. However, it resolves the interface's curvature more effectively than the small solid refinement, and in contrast to the curvature refinement, it discerns small and large features of equal curvature, thus avoiding refinement in regions of less importance. This feature has less effect today since Floefd now incorporates the real cell technology for cutting cells, which makes the corner cuts basically perfectly matched to the actual cat. This requires less refinement to capture more details in the CAD model, which means Floefd can perform very well capturing overall geometry and getting accurate results even with a relatively coarse mesh, allowing the user to concentrate more cells or add refinements in the more critical regions of the model where they are actually needed. Thanks for your attention.